The last section of this lesson deals with solving right triangles, and what that really means is that we're finding all 6 parts of the triangle. So in other words, I'm identifying what all 3 angles are, and I'm identifying what all 3 sides are. So if I look at the problem on the right, I've been given some information about some of those things. We have a 90-degree angle down here. That's one of my angles. I've got a 42-degree angle up here. That's another one of my angles. And I've been given the side of 70. So really I've got 3 out of the 6 things that I need to say that I've solved the right triangle. I'm going to use this 42-degree angle as my reference angle, and I'll show you one way to solve using that. And then we'll take a look at using another angle in just a second. So let's first of all look at that. Let's say I want to solve for this side, the hypotenuse of the triangle, based on this 42-degree reference angle. Well, I've got the hypotenuse that I'm trying to solve for, and then I've got this other side over here that I know is 70. And coming off this reference angle of 42 degrees, that would make the side of 70 the adjacent side, right? And therefore, if I'm trying to use the adjacent and hypotenuse, A and H, I use that with cosine. So the initial equation I would want to set up would be that the cosine of that 42-degree angle, cosine is adjacent over hypotenuse, so adjacent 70, and hypotenuse I'll just call HYP because that's the value I'm looking to find. Okay, and that the hypotenuse there is really my variable. So I'd multiply both sides by the hypotenuse to get it out of the denominator. So hypotenuse times the cosine of 42 degrees would be 70. And then I would divide both sides by the cosine of 42 degrees. So the hypotenuse equals 70 divided by cosine of 42 degrees. And then you plug that into your calculator. You should get a value that tells you the hypotenuse is approximately 94.2 units, whatever that is. I don't know if it's inches or centimeters or whatever else. So now I've got the adjacent side. I now have the hypotenuse side value. What I don't have is the opposite side. Okay, so the opposite side from 42 would be this. So I'll call it, I'll just call it opposite. I could call it x, I suppose. But if I'm comparing the opposite and adjacent side, I'm going to want to use tangent, right? Tangent is opposite over adjacent. Some of you might say, well, why don't we use the opposite side and hypotenuse now that we know it? We could use sine. And that's true, but keep in mind you would be using a slightly rounded number, which means there's a degree of error involved in this number, and as you use it in other places, you're gonna further multiply that error. So I would suggest setting it up with the 70 adjacent side that you already know. Okay, so we're going to say that the tangent of 42 degrees, tangent is opposite, which is 70, over, opposite on top, opposite over adjacent, which is 70, looks like that. And we do pretty much the same thing that we had done up above. We're going to multiply both sides by 70 to get it out of the denominator. 70 times the tangent of 42 degrees would then be equal to the opposite side. And when I plug 70 times tangent of 42 degrees, I find out that my opposite side would end up being approximately 63. All right, so now I've got all 3 sides. And you might say, well, I don't have all 3 angles, but that's easy enough, right? If this one's 90 and this one's 42, 180 minus 90 minus 42 would mean I'd have to have an angle down here of 48 degrees. Okay, so that one's not too tricky. I want to show you the other thing that we could have done, though. We could have started that way by saying we recognize that this angle has to be 48 degrees, and then we could do everything as a reference off of that angle. Okay, so if I had done that and I wanted to find this adjacent side, now I know we already did that. We found that side to be 63. In this case, coming off of this 48-degree reference angle, it would be the adjacent side. And this side over here would be the opposite side. Right? Since I know the adjacent and opposite, together those are tangent, I would say that the tangent of that 48-degree angle, opposite over adjacent, would be 70 over that missing side, assuming we didn't have it. Okay, multiply both sides by adjacent, the missing value there, tangent of 48, to get it out of the denominator, and then divide both sides by the tangent of 48. So the adjacent side must be 70 divided by the tangent of 48, whatever that value is. When you do that, and again, making sure your calculator is in degree mode, the adjacent side would come out to be about 63, which is what we said it was when we did it the other way. So I'm just showing you there's a couple different ways that you could get to these values. It's still indirect measurement using trig ratios, but it's going to be a different way to do it based on which one's your reference angle. Let's do the same thing using 48 as our reference angle, trying to find the hypotenuse. We already knew it was about 94.2, but we should be able to do it this way as well. I would set that up using sine, because I already know for sure the opposite side from 48, and I'm trying to find the hypotenuse. So I could say that sine of 48 is opposite, which is 70, over hypotenuse. Multiply both sides by the hypotenuse. So hypotenuse times the sine of 48 degrees equals 70. Divide both sides by that sine of 48 so that you got the hypotenuse all by itself. Hypotenuse equals 70 divided by the sine of 48. And when I plug that into my calculator, I was given a hypotenuse of approximately 94.2, which should, at this point, shouldn't be surprising, because that's what we already got using the other way. Okay, so a couple different ways that you could go about this. Don't feel like if you're doing something slightly different than a neighbor that you're in the wrong. As long as you're following these rules that go along with trig ratios, you'll be fine. All right, let's try the problem over on the right-hand side. So here we're missing two angles, x and y, and we don't know what the hypotenuse is either. In this problem, we're actually going to end up using the inverse functions as well. Let's start by trying to solve for this angle as our reference angle. And based on that angle, the sides that I know of are the side that's opposite it and the side that's adjacent to it. Opposite and adjacent tell me I could be using tangent. So I would initially set this up by saying the tangent of x is the opposite, 23, over the adjacent, which is 31. And so now I can undo that tangent in order to solve for x. I can undo that tangent by taking the arctangent. And if I do it to one side, I've got to do it to the other side. Okay, so the arctangent of the tangent of x is x. And the arctangent of 23 over 31 gives you an angle measurement of 36.6 degrees. Okay, so that's one of our angles. And now at that point, you might say, well, if this is 36.6 in here, and I know that this is 90, I should already be able to solve for y. And that's true. You could do that. If you want a little bit of practice with making use of these inverse trig ratios, you could also set something up with this angle as the reference angle, knowing that you've got the adjacent side to it and the opposite side. It looks similar. You could say that the tangent of y is the opposite, so 31, over the adjacent of 23, and take the arctangent of this side, so that I'm going to get y by itself, and the arctangent of this side. Okay, those will cancel essentially, and y will be equal to whatever the arctangent of 31/23 is, which is 53.4 degrees. Okay, and again, you could have solved that by maybe in an easier way by just saying 180 minus this 36.6 should get you the 53.4, and that's fine too. No, either one is fine. The only thing that we haven't really solved for at this point is the hypotenuse length. And you could do that really in a couple of different ways. If you're looking for the hypotenuse, you could compare that to, let's say you've got this angle over here that you know is 36.6. And you could say, well, let's compare that to the adjacent side. Adjacent hypotenuse is cosine. Okay, so I could say something like the cosine of this angle, which we now found out to be 36.6, is the adjacent side of 31 over hypotenuse. That would be one way to do it. I'm not going to complete that. You can if you want, but I'm going to show you another way that you could set it up. You could take a look at this angle now that you know it and try to compare the adjacent, well, let's say the opposite side over here to the hypotenuse. Opposite and hypotenuse are sine. Okay, so I could say that the sine of angle y, which we just found out to be 53.4 degrees, is the opposite, 31, over the hypotenuse. Okay, and there's a couple other variations that you could do. So you've got different options to work with once you know how to make use of all these trig ratios. Let's take a look at the last problem that we've got here. Okay, so this is a theater design, and you can see that the front of the stage over here, here's somebody sitting in the standing on their chair. You shouldn't do that. Sit down, you're going to get hurt. That's the front of the stage, and the back side of the stage is actually raised up a little bit. In some theaters they do this so that the audience can see everybody on stage a little bit better, not just the people in front. And that's called a raked stage. The stage is going to be a total of 30 feet long from front to back, and you see that marked in the diagram. And it's got a total rise of 2 feet, and you see that on the back side of the diagram here. Okay, that's going to form a right triangle, which is why we've got this little right angle marking there. A raked angle, so elevation of 5 degrees or less, is generally preferred for the safety and comfort of the actors. If you think about raising this up at an even higher angle, pretty soon they start tipping off the stage, right? We don't want that. Okay, so the question here is this rake stage that you're going to try to build like this within the range suggested? If you want it to be 30 feet long and you want it to be 2 feet raised up, does that meet within that 0 to 5 degree recommendation? So what we're going to do is set up what we know about trig ratios or inverse trig ratios to try to solve for this angle measurement. And if it's in between 0 degrees and 5 degrees, everything's good. If it's above 5 degrees, then we would say that this probably is not a very good stage to build, or it's not going to be real safe. So from that angle as my reference angle, the two values of the sides that I know are all the way across to the opposite side, which is 2 feet. And then I've also got the hypotenuse, which is 30 feet. Well, hopefully by now you're thinking through so, ka, toa, and recognizing that if I've got the opposite, O, and the hypotenuse, H, I'm dealing with so, sine. Okay, so my initial equation is going to be that the sine of that angle, which I don't know, I'm just going to call it sine of x, is going to be the opposite, which is 2, over the hypotenuse, which is 30. Now I'm going to undo this trig ratio so that I can find just x by itself. In order to undo that, I'm going to take the inverse sine of all of that, the arc sine of the sine of x. And if I do it to one side, I've got to do it to the other side. Okay, so over on this side, arc sine and sine cancel out. I'm left with x. And the arc sine of 2/30 ends up being 3.82 degrees. So to answer the question, this is a 3.82 degree angle, which means yes, the stage is safe because the angle falls between 0 degrees and 5 degrees, the recommendation for having a safe stage.